Right now, somewhere in the depths of space, there could be cosmic tunnels that connect distant regions of the universe, shortcuts through spacetime itself that could allow instantaneous travel between points separated by billions of light years. These aren't the wormholes of science fiction, but naturally occurring Einstein-Rosen bridges that emerge from the fundamental equations of general relativity, quantum field theory, and exotic physics that might be operating in cosmic environments we're only beginning to understand. We've always assumed that space is simply the stage where physics happens, a passive backdrop, through which matter and energy move according to predictable laws. We believe that the shortest distance between 2 points is always a straight line through three-dimensional space, and that traveling between distant cosmic locations requires journeying across every light year of intervening space. We were potentially wrong about the fundamental topology of spacetime and the cosmic, shortcuts that might naturally exist within it. Here is what makes this possibility so extraordinary. Wormholes aren't just theoretical curiosities dreamed up by imaginative physicists. They're direct mathematical consequences of Einstein's field equations, emerging naturally from the geometry of curved spacetime when matter and energy arrange themselves in specific configurations. The same equations that successfully describe black holes, gravitational waves, and cosmic expansion also predict the existence of spacetime tunnels that could connect widely separated regions of the universe. The mathematics behind natural wormhole formation are emerging from cutting-edge research in quantum gravity, string theory, and exotic matter physics. Theoretical physicists like Kip Thorne, Michael Morris, and Juan Maldacena have demonstrated that certain types of wormholes could theoretically form and remain stable under specific conditions, involving exotic matter quantum field effects or higher dimensional physics that might naturally occur in cosmic environments. But perhaps the most intriguing aspect of natural wormhole research is the growing evidence that the universe might contain the exotic physics necessary for wormhole formation and stabilization. Dark energy, quantum vacuum fluctuations, cosmic inflation physics, and other phenomena already accepted by mainstream cosmology involve exactly the types of exotic energy conditions that theoretical calculations suggest could support stable wormhole geometries. Recent theoretical breakthroughs have revealed that wormholes might form naturally during cosmic inflation, emerge from quantum fluctuations in spacetime geometry, develop at the centers of certain types of black holes, or arise from cosmic string interactions and other high-energy processes that occur throughout cosmic evolution. These aren't artificially constructed tunnels requiring advanced alien technology. They are potential natural features of cosmic architecture that emerge from fundamental physics. Tonight, we'll explore the theoretical foundations for natural wormhole formation, examine the exotic physics that could stabilize cosmic spacetime tunnels, and investigate the observational signatures that might reveal wormhole presence in our universe. We'll journey through Einstein's spacetime geometry, quantum field theory in curved backgrounds, and the cutting-edge physics that suggest natural wormholes might be far more plausible than previously imagined. We'll discover how cosmic inflation could have created primordial wormholes that persist to the present day, investigate how quantum entanglement might be fundamentally connected to wormhole geometry, and explore the possibility that black holes might actually be one end of cosmic tunnels that connect to distant regions of spacetime. We'll examine the observational strategies astronomers are developing to search for natural wormhole signatures and the revolutionary implications their discovery would have for physics, cosmology, and our understanding of cosmic connectivity. By the end of this exploration, you will all understand why some of the most respected physicists in the world believe that natural wormholes represent a serious possibility rather than science fiction fantasy, why the universe might naturally produce spacetime shortcuts that connect distant cosmic regions, and what it would mean to live in a cosmos where the apparent separations between distant locations are illusory due to hidden cosmic tunnels. This isn't speculation about far future technology or alien engineering projects. This is cutting-edge physics exploring whether the universe itself might naturally create shortcuts through spacetime using exotic matter, quantum effects, and gravitational dynamics that operate according to the fundamental laws of physics. The cosmic tunnels we're investigating emerge directly from our most successful theories of spacetime, gravity, and quantum mechanics. The implications extend far beyond academic physics. If natural wormholes exist, they would revolutionize our understanding of cosmic connectivity, the relationship between distant regions of the universe, and the fundamental nature of space and time. They could explain mysterious astronomical observations, provide natural mechanisms for cosmic evolution, and reveal that the universe is far more interconnected than our local three-dimensional perspective suggests. If you're ready to explore how space-time tunnels could naturally exist in our universe, subscribe and hit the thumbs up button. And here is a question that will transform your perspective. If natural wormholes connect distant regions of space-time, could some of the mysterious cosmic phenomena we observe actually be evidence for cosmic tunnels we don't yet recognize? Share your thoughts in the comments. I'll pin the most insightful response. The physics of natural wormhole formation is about to reveal why cosmic shortcuts through space-time might not be science fiction but natural consequences of exotic physics that could be operating throughout the universe right now. What you're about to learn will transform your understanding of space-time geometry, cosmic connectivity, and the possibility that the universe contains hidden tunnels that make distant regions of space much closer than they appear. Now, let's begin our journey into the physics that could make natural wormholes a cosmic reality. Chapter 1. Einstein's spacetime bridges. The possibility of natural wormholes begins with Albert Einstein's revolutionary description of gravity as curved spacetime geometry, where massive objects create warps and distortions in the fabric of space and time that can produce exotic geometrical structures, including tunnels that connect distant regions of the universe. Einstein's field equations don't just allow wormholes. They practically demand their existence under specific conditions involving matter and energy configurations that might occur naturally in cosmic environments. Einstein and Nathan Rosen discovered the first theoretical wormhole in 1935 while investigating the mathematical properties of black hole spacetime geometry. Their analysis of the Schwarzschild solution, the spacetime around a spherically symmetric massive object, revealed that the equations describing black hole interiors could be extended to describe bridges connecting two different regions of spacetime. These Einstein-Rosen bridges represented the first rigorous mathematical demonstration that spacetime geometry itself could form tunnels between distant locations. The geometry of an Einstein-Rosen bridge emerges from the remarkable mathematical structure of black hole spacetime. When you follow the equations describing spacetime curvature inside a black hole event horizon, the mathematics reveals that the interior doesn't end at a central singularity, as intuition might suggest, but instead connects to another region of spacetime through a geometric bridge. This connection exists not in ordinary three-dimensional space, but in the four-dimensional spacetime geometry described by general relativity. The Schwarzschild wormhole, as the Einstein-Rosen bridge is technically known, represents a non-traversable spacetime tunnel, a cosmic bridge that connects distant regions but cannot be used for travel because the bridge itself collapses too quickly for anything to pass through it. The wormhole throat pinches closed at the speed of light, creating a dynamic geometric structure that connects distant spacetime regions while remaining practically inaccessible to matter or information transfer. However, the mathematical discovery of Einstein-Rosen bridges demonstrated that spacetime topology could be far more complex than three-dimensional intuition suggests. The equations of general relativity permit spacetime geometries where distant regions become connected through higher dimensional pathways that bypass the usual three-dimensional routes between locations. This geometric possibility represents a fundamental feature of curved spacetime rather than an exotic anomaly. John Wheeler's later work on spacetime foam in the 1950s and 1960s extended wormhole concepts to quantum scales, proposing that the geometry of spacetime itself might be riddled with microscopic wormhole structures at the Planck length scale, where quantum gravitational effects become important. Wheeler, as spacetime foam, suggests that the apparently smooth geometry of spacetime on large scales might actually consist of a complex network of quantum wormholes at the smallest scales. The Wheeler wormholes would exist at scales of approximately 10 to 35 meters and lifetimes of about 10 to 43 seconds, dimensions and timescales where quantum uncertainty dominates gravitational physics. These microscopic spacetime tunnels would constantly form and dissolve due to quantum fluctuations, creating a dynamic foam-like structure in spacetime geometry that could potentially be enlarged or stabilized through exotic physics processes. Modern theoretical physics has revealed that wormhole geometries can arise from many different types of matter and energy distributions, not just the specific black hole configurations that Einstein and Rosen originally investigated. Rotating black holes described by the Kerr metric, electrically charged black holes described by the Reissner-Nordstrom metric, and even more exotic spacetime geometries can contain wormhole-like structures that connect different regions of spacetime. The mathematical classification of wormhole types reveals remarkable diversity in possible spacetime tunnel geometries. Traversable wormholes allow matter and information to pass through them, while non-traversable wormholes connect spacetime regions without permitting travel. Intra-universe wormholes connect different locations within the same universe, while inter-universe wormholes could theoretically connect our universe to entirely different cosmic domains with potentially different physics. Lorentzian wormholes exist in normal spacetime with the familiar signature of one time dimension and three space dimensions, while Euclidean wormholes exist in imaginary time and play important roles in quantum gravity calculations and cosmological models. The diversity of wormhole geometries suggests that spacetime tunnels could arise from many different physical processes and exist in many different forms throughout cosmic evolution. The throat geometry of wormholes represents their most crucial structural feature, the narrowest point of the spacetime tunnel that determines whether the wormhole can be traversed and what types of matter or energy can pass through it. The throat's geometric properties depend on the exotic matter or energy fields that support the wormhole structure, creating relationships between wormhole physics and fundamental particle physics or quantum field theory. Embedding diagrams provide powerful visualizations of wormhole geometry by representing curved spacetime as surfaces embedded in higher dimensional space. These diagrams reveal how wormholes create shortcuts through spacetime by connecting distant regions through paths that are shorter than any route through ordinary three-dimensional space. The geometric elegance of these structures demonstrates how general relativity naturally accommodates spacetime connectivity that transcends three-dimensional limitations. The stability of Einstein-Rosen bridges depends on sophisticated mathematical analysis of how small perturbations affect wormhole geometry. Classical Einstein-Rosen bridges prove unstable to even tiny disturbances, collapsing before any signal can traverse them. However, this instability occurs in classical general relativity without considering quantum effects, exotic matter, or other physics that might naturally stabilize wormhole structures. Contemporary research has identified specific conditions under which wormhole geometries could remain stable for extended periods or even permanently. These stabilization mechanisms involve exotic matter with negative energy density, quantum field effects that modify spacetime geometry, or higher dimensional physics that could naturally occur in cosmic environments, where standard general relativity receives corrections from quantum gravity or string theory effects. The ADS-CFT correspondence in theoretical physics has revealed deep connections between wormhole geometry and quantum entanglement, suggesting that Einstein-Rosen bridges might be fundamentally related to quantum mechanical phenomena rather than purely classical gravitational effects. This relationship implies that wormhole formation might be intimately connected to quantum information theory and the fundamental structure of quantum entanglement. Spacetime topology change represents one of the most exotic aspects of wormhole physics, involving processes where the basic connectivity structure of spacetime itself changes over time. Wormhole formation, evolution, and collapse represent examples of topology change that challenge our understanding of causality, information conservation, and the relationship between geometry and physics in gravitational systems. The energy conditions of general relativity requirements that matter and energy satisfy specific mathematical constraints to produce physically reasonable spacetime. Geometries reveal that most naturally occurring matter cannot support stable wormhole geometries without exotic modifications. However, quantum field theory, cosmological physics, and speculative theories beyond the standard model suggest various mechanisms through which these energy conditions might be violated in natural cosmic environments. As you contemplate Einstein's mathematical discovery that spacetime geometry naturally accommodates tunnels connecting distant regions, recognize that wormholes represent direct consequences of our most successful theory of gravity and spacetime. The same equations that accurately describe planetary orbits, black hole mergers, and cosmic expansion also predict the existence of spacetime bridges that could fundamentally alter our understanding of cosmic connectivity and the nature of space and time. The mathematical foundations Einstein established for wormhole physics continue to inspire cutting-edge research into whether natural processes could create and maintain cosmic tunnels through spacetime. But mathematics alone cannot determine whether wormholes actually exist. We must explore the exotic physics that could make spacetime bridges a natural feature of cosmic architecture. Chapter 2: Exotic Matter and Energy. The formation and stability of natural wormholes requires exotic forms of matter and energy that violate the CONVENTIONAL energy conditions of general relativity substances with negative energy density, negative pressure, or other properties that seem to contradict our everyday experience of physics, but might naturally occur in quantum field theory, cosmological evolution, and extreme gravitational environments throughout the universe. The null energy condition, weak energy condition, and strong energy condition represent mathematical requirements that ordinary matter must satisfy to produce physically reasonable spacetime geometries in general relativity. These conditions essentially require that energy density remain positive and that matter cannot move faster than light when measured by local observers. However, stable wormhole geometries require violations of these energy conditions, demanding exotic matter with properties that ordinary particles and fields cannot provide. Negative energy density represents the most crucial requirement for wormhole stabilization, creating gravitational effects that oppose the natural tendency of spacetime tunnels to collapse under their own geometric instability. Unlike ordinary matter, which creates attractive gravitational effects that tend to curve spacetime inward, negative energy density creates repulsive gravitational effects that can hold wormhole throats open against collapse. This exotic matter must be precisely distributed throughout the wormhole structure to maintain geometric stability. The Casimir effect provides the most well-established example of negative energy density in quantum field theory, demonstrating that quantum vacuum fluctuations can create regions of space where energy density falls below the vacuum energy level of empty space. When two parallel conducting plates are placed very close together, quantum fields between the plates have fewer allowed modes than in free space, creating a region of negative energy density that produces measurable attractive forces between the plates. Quantum field theory in curved spacetime reveals that negative energy densities can arise naturally in gravitational environments through mechanisms that have no analog in flat spacetime physics. The Hawking radiation process that causes black hole evaporation involves negative energy density near the event horizon, while the Unruh effect predicts that accelerated observers will detect thermal radiation even in apparently empty space. These effects suggest that exotic energy conditions might occur naturally in cosmic environments. Quintessence and phantom dark energy models propose that cosmic acceleration could be driven by scalar fields with equation of state parameters that violate energy conditions on cosmic scales. If phantom dark energy exists with W-1, where W is the ratio of pressure to energy density, it would possess the exotic properties needed to support wormhole geometries. Since dark energy comprises about 68% of the universe's total energy content, phantom energy could provide a cosmic reservoir of exotic matter. The inflated field that drives cosmic inflation in the early universe exhibits many properties similar to those required for wormhole stabilization, including the ability to create exponential expansion of space and to maintain nearly constant energy density over vast regions. Some theoretical models suggest that inflation physics could naturally produce both cosmic expansion and stable wormhole structures through different phases of scalar field evolution. Cosmic strings, one-dimensional topological defects that could form during phase transitions in the early universe, represent another potential source of exotic matter for wormhole formation. These hypothetical objects would have enormous energy density, concentrated into string-like structures with gravitational effects that could warp spacetime sufficiently to create wormhole geometries. Cosmic string interactions might naturally produce the complex energy distributions needed for spacetime tunnel formation. Quantum corrections to general relativity suggest that exotic matter effects might arise naturally from quantum gravitational phenomena that become important at high energy scales or in strong gravitational fields. Loop quantum gravity, for example, predicts that quantum geometry effects could create effective exotic matter distributions that violate classical energy conditions while preserving the fundamental principles of quantum mechanics and relativity. String theory provides theoretical frameworks for exotic matter through mechanisms including extra-dimensional physics, supersymmetry breaking, and the complex interactions between different types of strings and branes. Some string theory models predict the existence of exotic matter fields that could naturally arise from higher dimensional physics and could potentially support stable wormhole geometries without violating fundamental principles of string theory. The holographic principle emerging from black hole thermodynamics and ADS-CFT correspondence suggests that exotic matter effects might arise from information theoretic constraints on spacetime geometry rather than from fundamental particle physics. If spacetime geometry is determined by quantum information processing on lower dimensional boundaries, then exotic energy conditions might emerge naturally from holographic physics rather than requiring artificially constructed matter distributions. Vacuum metastability in quantum field theory could provide mechanisms for creating regions of negative energy density if the universe exists in a false vacuum state that could decay to lower energy configurations. During such vacuum decay processes, the interface regions between different vacuum states could exhibit exotic energy properties that might naturally support wormhole formation and stabilization. Modified gravity theories, including FR gravity and extra-dimensional models, can create effective exotic matter distributions through geometric modifications to Einstein's S-field equations rather than through exotic matter fields. These theories suggest that apparent violations of energy conditions might actually reflect our incomplete understanding of gravitational physics on cosmic scales, rather than requiring truly exotic matter. Quantum entanglement effects in curved spacetime might create non-local correlations that effectively produce exotic energy distributions capable of supporting wormhole geometries. Recent research into the relationship between quantum entanglement and spacetime geometry suggests that entangled quantum states might naturally create the types of non-local energy correlations that wormhole stabilization requires. The vacuum expectation value of the stress energy tensor in quantum field theory can become negative in curved spacetime backgrounds, providing natural mechanisms for creating the exotic matter distributions that wormhole physics requires. These quantum field effects arise automatically in gravitational environments and don't require artificial exotic matter construction or violations of fundamental physical principles. Dynamical Casimir effects occur when boundary conditions for quantum fields change rapidly with time, creating particle production and negative energy density distributions that could potentially support spacetime tunnel formation. These effects might occur naturally during rapid gravitational collapse, cosmic phase transitions, or other high-energy astrophysical processes that involve rapidly changing spacetime geometries. Traversable wormhole stabilization requires not just negative energy density, but precise control over the distribution and dynamics of exotic matter throughout the wormhole structure. The exotic matter must be arranged to create stable equilibrium between gravitational attraction that tends to collapse the wormhole and exotic matter repulsion that holds the throat open, requiring sophisticated balance between competing forces. The total amount of exotic matter needed for wormhole stabilization depends on the size and geometry of the spacetime tunnel, with larger wormholes generally requiring more exotic matter for stability. Microscopic quantum wormholes might require only tiny amounts of exotic matter that could arise from quantum fluctuations, while macroscopic cosmic wormholes would require exotic matter distributions on scales comparable to stellar or galactic mass concentrations. Analog gravity systems, condensed matter systems that exhibit dynamics analogous to general relativistic spacetime, have been used to create laboratory analogs of wormhole physics using exotic matter distributions in systems like Bose-Einstein condensates and nonlinear optical media. These experiments demonstrate that exotic matter effects can indeed create geometric structures analogous to spacetime tunnels in controllable laboratory environments. As you consider the exotic matter requirements for natural wormhole formation, recognize that quantum field theory, cosmological physics, and advanced gravitational theories all predict mechanisms through which exotic energy conditions might arise naturally in cosmic environments. The universe already contains dark energy with exotic properties, quantum vacuum effects that create negative energy densities, and high-energy processes that could naturally produce the exotic matter distributions that spacetime tunnels require. But exotic matter represents just one aspect of natural wormhole physics. We must now explore how quantum mechanics fundamentally connects to wormhole geometry and might provide natural mechanisms for spacetime tunnel formation. Chapter 3. Quantum entanglement bridges the deepest connection between quantum mechanics and wormhole physics emerges through the revolutionary discovery that quantum entanglement, the spooky action at a distance that Einstein found so troubling, might be fundamentally equivalent to Einstein-Rosen bridges, suggesting that natural wormhole formation could arise directly from quantum mechanical processes rather than requiring exotic matter engineering or artificial spacetime manipulation. This quantum geometric duality implies that wormholes are not merely gravitational curiosities, but fundamental features of quantum spacetime. The A equals EPR conjecture, proposed by Juan Maldacena and Leonard Susskind, establishes a precise mathematical equivalence between Einstein-Rosen bridges, and Einstein-Podolsky-Rosen quantum entanglement, EPR. This correspondence suggests that every pair of entangled particles is connected by a microscopic wormhole through spacetime, and conversely, that every wormhole represents the geometric manifestation of quantum entanglement between its two endpoints. Quantum entanglement typically involves pairs of particles that share quantum states in ways that cannot be explained by classical physics, creating instantaneous correlations between measurements performed on widely separated particles. When you measure the quantum state of one entangled particle, you instantly determine the state of its partner, regardless of the spatial separation between them. This non-local correlation appears to violate the speed of light limitation on information transmission, but doesn't actually allow faster-than-light communication. The geometric interpretation of quantum entanglement through wormhole physics suggests that entangled particles remain connected through microscopic spacetime tunnels that exist at the Planck scale, about 1035 meters, where quantum gravitational effects become important. These quantum wormholes would provide geometric pathways through which quantum correlations propagate, explaining the apparent instantaneous nature of entanglement through genuine spacetime connectivity, rather than mysterious action at a distance. Thermofield double states in quantum field theory provide mathematical frameworks for understanding how quantum entanglement creates geometric connections through spacetime. These states describe quantum fields that exist in thermal equilibrium across two disconnected regions of spacetime, creating quantum correlations that correspond precisely to wormhole bridges connecting those regions. The mathematical structure of thermofield double states reveals deep connections between quantum information theory and spacetime geometry. The holographic principle, emerging from black hole physics and string theory, suggests that quantum entanglement plays a fundamental role in generating spacetime geometry itself. If spacetime emerges from quantum entanglement networks, rather than being a fundamental arena within which quantum mechanics operates, then wormhole formation represents a natural consequence of quantum entanglement dynamics, rather than an exotic gravitational phenomenon requiring special conditions. Quantum error correction codes provide surprising insights into wormhole physics by revealing how quantum information can be distributed across multiple subsystems in ways that maintain coherence even when individual subsystems are lost or damaged. The mathematical structure of quantum error correction corresponds precisely to the geometry of wormholes in anti-de Sitter spacetime, suggesting deep connections between information theory and gravitational physics. The Ruttakian-Nagy correspondence establishes precise relationships between quantum entanglement entropy in boundary quantum field theories and in areas of minimal surfaces in higher dimensional gravitational theories. This correspondence reveals that quantum entanglement naturally creates geometric structures in higher dimensional spacetime that correspond to wormhole-like connections, providing evidence that entanglement and spacetime geometry are fundamentally linked. Quantum teleportation protocols, which allow quantum states to be transmitted between distant locations using entanglement and classical communication, might represent operational descriptions of how information traverses quantum wormholes. The fact that quantum teleportation preserves quantum information while destroying the original state corresponds to how wormhole traversal might preserve information content while transforming the physical substrate that carries that information. Entanglement swapping experiments demonstrate that quantum entanglement can be transferred between particle pairs that have never directly interacted, creating extended entanglement networks that span multiple particles across large distances. These networks could correspond to complex wormhole geometries that connect multiple spacetime regions through branching tunnel structures, suggesting that natural quantum processes might create intricate spacetime connectivity patterns. The black hole information paradox, the apparent conflict between quantum mechanics and general Relativity regarding what happens to information that falls into black holes receives potential resolution through quantum entanglement wormhole connections. If black holes are connected to other regions of spacetime through quantum wormholes, then information could escape black hole destruction through quantum tunneling processes that preserve information conservation while allowing black hole evaporation. Quantum monogamy theorems limit how much entanglement can be shared between multiple quantum systems, creating constraints on wormhole network geometries that correspond precisely to geometric restrictions on spacetime connectivity in general relativity. These quantum information constraints provide natural explanations for why certain wormhole configurations are forbidden while others are allowed, connecting quantum mechanics to spacetime topology. The emergence of spacetime from quantum entanglement suggests that wormhole formation might be an automatic consequence of quantum field dynamics rather than requiring special initial conditions or exotic matter distributions. If spacetime geometry emerges from underlying quantum entanglement networks, then changes in entanglement structure naturally create changes in spacetime connectivity, potentially explaining how natural wormholes could form and evolve through quantum processes. Quantum computational complexity theory provides new perspectives on wormhole physics by revealing connections between the difficulty of quantum computational tasks and the geometric properties of wormholes in holographic spacetimes. The growth of computational complexity over time corresponds to wormhole growth behind black hole horizons, suggesting that quantum computation and spacetime geometry share fundamental structural relationships. Bell's inequality violations in quantum mechanics demonstrate that entangled systems exhibit correlations that cannot be explained by any local classical theory, requiring either faster-than-light influences or non-local hidden variables. The wormhole interpretation of entanglement provides a geometric explanation for these non-local correlations through genuine spacetime connections that respect relativity while creating apparent non-locality in three-dimensional space. Quantum field theory in curved spacetime predicts that particle creation and entanglement naturally occur in time-varying gravitational fields, such as those present during black hole formation, cosmic inflation, or gravitational wave propagation. These processes could naturally create entangled quantum states that correspond to wormhole connections, suggesting that gravitational dynamics automatically generate spacetime tunnel networks. The many-worlds interpretation of quantum mechanics might connect to wormhole physics through mechanisms that create tunnels between different branches of the quantum multiverse. If quantum measurement creates new branches of reality, then wormholes might provide connections between these branches, allowing information or even matter transfer between different quantum worlds through spacetime geometry modifications. Quantum chromodynamics, the theory of the strong nuclear force, exhibits phenomena like color confinement and flux tubes that share mathematical similarities with wormhole physics. The strong force creates string-like connections between quarks that cannot be broken by increasing separation distance, analogous to how wormholes create geometric connections between distant spacetime regions that persist regardless of coordinate distance. Spontaneous quantum entanglement generation occurs naturally in many quantum field theory processes, including particle pair creation, vacuum fluctuations, and phase transitions. If these natural entanglement generation processes correspond to wormhole formation through the A equals EPR correspondence, then natural wormholes might form automatically wherever quantum field dynamics create entangled states. The quantum Zeno effect, which can freeze quantum evolution through frequent measurements, might provide mechanisms for stabilizing quantum wormholes by preventing the quantum tunneling processes that could cause wormhole collapse. Natural cosmic processes that create effective quantum measurements could potentially stabilize wormhole networks without requiring artificial intervention or exotic matter engineering. As you contemplate the deep connections between quantum entanglement and spacetime geometry, recognize that these relationships suggest wormhole formation is not an exotic gravitational anomaly, but a fundamental feature of quantum spacetime. Every quantum entanglement event in the universe might create microscopic wormhole connections that could potentially grow, stabilize, or network into larger-scale spacetime tunnel systems through natural quantum and gravitational processes. But quantum mechanics represents just one pathway to natural wormhole formation. We must now explore how cosmic inflation, the rapid expansion of space in the early universe, could have naturally produced wormholes that persist to the present day. Chapter 4. Primordial Wormhole Formation. The extraordinary physics of cosmic inflation, the period of exponential expansion that occurred in the first fraction of a second after the Big Bang, might have naturally produced countless wormholes that could persist throughout cosmic evolution, creating a hidden network of space-time tunnels that connect distant regions of our universe and potentially other cosmic domains. This primordial wormhole formation represents one of the most plausible mechanisms for natural wormhole creation, emerging from the same physics that explains cosmic flatness, homogeneity, and the origin of cosmic structure. Cosmic inflation involves scalar field dynamics that create exponential expansion of space while generating quantum fluctuations that become the seeds for all cosmic structure formation. The inflated field that drives cosmic expansion possesses many properties similar to those required for wormhole formation, including the ability to create regions of space with exotic energy conditions and to generate complex topological structures through phase transitions and field dynamics. Quantum fluctuations during inflation naturally create regions where the inflated field takes different values, leading to variations in expansion rate and spacetime curvature that could evolve into wormhole geometries. When inflation ends through processes like preheating or reheating, these quantum fluctuations could leave behind topological defects including cosmic strings, domain walls, and potentially wormhole structures that remain embedded in post-inflationary spacetime. The horizon problem in standard Big Bang cosmology, why distant regions of the universe appear to have the same temperature, despite never being in causal contact, receives elegant explanation through inflation physics. However, inflation also creates the possibility that regions of space which appear causally disconnected in post-inflationary coordinates could remain connected through wormhole bridges created during the inflationary epoch. Eternal inflation scenarios suggest that cosmic inflation continues indefinitely in most regions of space while ending locally to create pocket universes like our observable cosmos. This process could naturally create wormhole connections between different pocket universes, allowing travel or communication between cosmic domains that appear completely disconnected from the perspective of any single universe's physics and observation capabilities. False vacuum decay during inflation could create bubble nucleation events where different regions of space transition to different vacuum states with potentially different physics. The boundaries between these vacuum regions could evolve into wormhole geometries that connect cosmic domains with different physical constants, particle content, or effective dimensionalities, creating a cosmic multiverse connected by spacetime tunnels. Topological inflation models propose that cosmic expansion could naturally create complex topological structures in spacetime geometry, including handles, bridges, and tunnel-like connections that correspond to wormhole formation. These models suggest that the rapid stretching of space during inflation could transform microscopic quantum fluctuations in spacetime topology into macroscopic geometric features that persist after inflation ends. The inflationary production of primordial black holes through large amplitude density fluctuations could simultaneously create wormhole structures if the collapse conditions produce exotic spacetime geometries. rather than simple black hole formation. Some theoretical models suggest that primordial black holes might actually be one end of Einstein-Rosen bridges that connect to distant spacetime regions through naturally formed cosmic tunnels. Cosmic string formation during inflation represents one of the most well-studied mechanisms for creating topological defects that could evolve into wormhole structures. When cosmic strings intersect or undergo complex dynamical evolution, they could create closed-loop structures that collapse in ways that produce wormhole geometries rather than simply disappearing through gravitational wave emission or other conventional string evolution processes. Pre-Big Bang cosmology models suggest that our universe might have emerged from gravitational collapse in a higher dimensional space, potentially creating natural wormhole connections between pre-existing cosmic regions and the post-Big Bang spacetime that we inhabit. These models propose that wormhole formation represents a fundamental aspect of cosmic birth, rather than a rare accident of particular matter distributions. Chaotic inflation scenarios involve multiple phases of inflation with different field values and expansion rates that could naturally create complex spacetime geometries, including wormhole structures. As different regions of space undergo inflation at different rates and times, the resulting spacetime could contain tunnel-like connections between regions that experience different inflationary histories. The string theory landscape of possible vacuum states suggests that inflation could explore many different regions of this landscape, potentially creating wormhole connections between spacetime regions that stabilized in different vacuum configurations. Each vacuum state could support different physics, making these primordial wormholes into cosmic bridges between regions with fundamentally different natural laws. Quantum cosmology calculations of the wave function of the universe predict that spacetime could naturally emerge from quantum fluctuations with complex topological structure, including wormhole-like connections. The Hartle-Hawking no-boundary proposal and other quantum cosmology models suggest that the universe's quantum origin might automatically include spacetime tunnel formation as a generic feature. Brane cosmology scenarios propose that our four-dimensional spacetime exists as a lower-dimensional surface embedded in higher-dimensional space, with inflation occurring through brane dynamics in the higher-dimensional bulk. Brane collisions, intersections, or complex evolution could naturally create wormhole connections between different brane regions or between branes and the higher-dimensional bulk space. The graceful exit problem in inflation, how cosmic expansion transitions from exponential inflation to radiation-dominated cosmic evolution might involve phase transitions that naturally create wormhole structures as byproducts of the mechanism that ends inflation. These phase transitions could simultaneously explain inflation termination and primordial wormhole production through unified physics. Curvature fluctuations generated during inflation could evolve into closed wrapped surfaces that form primordial black holes. But under specific conditions, these same fluctuations might create wormhole throats instead of black hole horizons. The distinction between black hole and wormhole formation depends on subtle details of the gravitational collapse process that determines whether trapped surfaces close completely or remain connected to other spacetime regions. Loop quantum cosmology modifications to the Big Bang singularity suggest that cosmic expansion might emerge from quantum gravitational effects that replace the classical singularity with a quantum bounce connecting to pre-existing spacetime. This bounce could naturally create wormhole bridges between pre-bounce and post-bounce cosmic epochs, making our universe's birth simultaneously a connection to previous cosmic cycles. Observational signatures of primordial wormhole formation could include specific patterns in cosmic microwave background fluctuations, gravitational wave backgrounds from wormhole dynamics, or correlations in cosmic structure that reflect wormhole-mediated connections between apparently causally disconnected regions. Future precision cosmology observations might reveal evidence for wormhole networks created during inflation. The anthropic principle gains new dimensions in primordial wormhole scenarios because regions of space connected by spacetime tunnels could share information and potentially coordinate evolution in ways that would not be possible if cosmic regions were completely causally isolated. This coordination could affect the probability of observer formation and could explain apparent fine-tuning of cosmic parameters. Primordial wormhole evolution after inflation would depend on complex interactions between wormhole geometry and post-inflationary cosmic expansion, matter formation, and structure formation processes. Some primordial wormholes might grow with cosmic expansion, while others could shrink or collapse, creating a dynamic wormhole network that evolves throughout cosmic history. The hierarchy problem in particle physics, why gravity is so much weaker than other fundamental forces, might receive explanation through primordial wormhole formation if gravitational effects can propagate through higher dimensional wormhole networks, while other forces remain confined to four-dimensional spacetime. This could explain gravity's apparent weakness through geometric effects rather than fundamental force-strength differences. As you contemplate the possibility that cosmic inflation naturally created countless wormholes throughout our universe, recognize that this represents one of the most plausible mechanisms for natural spacetime tunnel formation. The same extraordinary physics that explains cosmic expansion, structure formation, and the origin of everything we observe might have simultaneously created a hidden network of cosmic shortcuts that connect distant regions through spacetime geometry we cannot directly observe. But primordial formation represents just one pathway to natural wormhole creation. We must now explore how black holes themselves might be fundamentally connected to wormhole physics in ways that could make spacetime tunnels a common feature of cosmic evolution. Chapter 5. Black hole connections. Black holes might not be the cosmic dead ends we've always imagined, but rather one end of natural wormhole, tunnels that connect to distant regions of spacetime, other universes, or exotic geometric structures that make these gravitational monsters into cosmic gateways rather than inescapable prisons. This revolutionary perspective on black hole physics emerges from advanced theoretical research suggesting that event horizons might hide wormhole throats that connect black hole interiors to completely different spacetime regions. The traditional view of black holes describes them as regions of spacetime where gravitational curvature becomes so extreme that nothing, not matter, not light, not information, can escape once it crosses the event horizon. The interior of a black hole is thought to contain a central singularity where spacetime, curvature, and density become infinite, creating conditions that violate the known laws of physics and terminate all causal pathways that enter from the outside universe. However, this conventional picture faces serious challenges from quantum mechanics, information theory, and advanced studies of black hole spacetime geometry. The black hole information paradox, the apparent conflict between general relativity and quantum mechanics regarding the fate of information that falls into black holes, has led physicists to reconsider whether black hole interiors might be more complex than classical general relativity suggests. The fuzzball proposal in string theory suggests that black holes might not contain classical spacetime interiors at all, but instead consist of complex quantum geometric structures that could include wormhole-like connections to other regions of spacetime. String theory calculations indicate that black hole microstates, the quantum mechanical degrees of freedom that account for black hole entropy, might naturally organize themselves into geometric configurations that connect to distant spacetime locations. ADS-CFT correspondence, one of the most powerful dualities in theoretical physics, establishes precise relationships between gravitational theories containing black holes and quantum field theories without gravity. This correspondence suggests that black hole interiors might be dual to quantum entanglement between different regions of the boundary field theory, implying that black holes create genuine spacetime connections rather than isolated gravitational prisons. The Einstein-Rosen bridge interpretation of black holes proposes that the Schwarzschild solution describing spherically symmetric black holes actually describes wormhole structures that connect two asymptotic regions of spacetime. In this view, what we observe as a black hole represents one mouth of a wormhole tunnel, with the other mouth existing in a distant region of space, or even a separate universe that remains causally disconnected from our observable cosmos. Rotating black holes described by the Kerr metric exhibit even more complex geometric structure that could naturally accommodate wormhole connections. The Kerr solution contains regions called ergospheres, where spacetime itself is dragged around the rotating black hole, creating complex causal structures that might naturally evolve into traversable wormhole geometries under specific conditions, involving quantum corrections or exotic matter interactions. The holographic principle applied to black holes suggests that all information contained within a black hole can be encoded on its two-dimensional event horizon surface, implying that black hole interiors might be emergent geometric features that arise from quantum information processing on the horizon. This information geometric correspondence could naturally explain how black holes connect to other spacetime regions through holographic wormhole networks. Hawking radiation, the thermal emission that causes black holes to evaporate over time, might actually represent evidence for wormhole connections between black hole interiors and the external universe. Some theoretical models propose that Hawking radiation emerges not from vacuum fluctuations near the event horizon, but from quantum entanglement between the black hole interior and distant spacetime regions connected through wormhole geometry. The black hole firewall paradox, a conflict between different principles of quantum mechanics and general relativity applied to black hole physics, could receive resolution if black holes contain wormhole structures that allow information to escape through channels that do violate the principles that create the firewall paradox. Wormhole connections could provide escape routes for information that preserve quantum mechanics while respecting general relativistic constraints. Primordial black hole formation in the early universe could have naturally created wormhole networks if the gravitational collapse conditions that form these ancient black holes simultaneously produce spacetime tunnel structures. Primordial black holes might represent the observable ends of wormhole bridges that connect to distant cosmic regions, or even other universes formed during different phases of cosmic evolution. The no-hair theorem of black hole physics states that black holes are characterized completely by their mass, electric charge, and angular momentum, implying that all other information about matter that formed them is lost. However, this theorem applies only to classical black holes in pure general relativity, and quantum effects or wormhole connections could preserve additional information about black hole formation and evolution. Black hole mergers detected by gravitational wave observatories like LIGO and Virgo involve the collision and reconnection of wormhole structures rather than simple collision of isolated gravitational objects. The complex gravitational wave signals observed from black hole mergers might contain information about wormhole geometry evolution during these cosmic collisions, providing observational clues about black hole wormhole connections. The information paradox resolution through black hole complementarity proposes that information simultaneously falls into black holes and escapes through Hawking radiation, depending on the reference frame of the observer. Wormhole connections could provide the geometric mechanism that makes complementarity physically realizable by allowing information to reach both black hole interior and exterior regions through spacetime tunnel pathways. Quantum tunneling effects in black hole physics might allow particles and information to escape from black hole interiors through wormhole connections, even when classical general relativity predicts escape to be impossible. These quantum geometric effects could modify black hole physics in ways that transform isolated gravitational objects into connected components of cosmic wormhole networks. The stretched horizon formalism in black hole physics describes how infalling matter appears to external observers to be spread across the event horizon's surface and thermalized into a quantum state that preserves information while appearing to disappear. This formalism could naturally accommodate wormhole connections that allow the thermalized information to propagate to distant spacetime regions through geometric tunnels. White holes, hypothetical objects that represent time-reversed versions of black holes, could be connected to black holes through wormhole bridges, creating cosmic structures where matter falling into black holes emerges from white holes in distant spacetime regions. While white holes have never been observed, they represent mathematically valid solutions to Einstein's equations that could naturally arise if black holes possess wormhole interiors. The Susskind-Thorlacius model of black hole formation and evaporation incorporates string theory effects that could naturally create wormhole structures as black holes evolve from formation through complete evaporation. This model suggests that black hole evolution automatically produces spacetime connectivity that connects black hole formation regions to the locations where Hawking radiation emerges. Black hole interior reconstruction in holographic theories reveals how quantum information theory determines the geometric structure of spacetime regions behind event horizons. These reconstruction techniques suggest that black hole interiors emerge from quantum entanglement patterns that naturally correspond to wormhole geometries connecting black holes to other spacetime regions. The page curve describing how black hole entropy evolves during evaporation predicts that information begins to emerge from black holes when they have lost approximately half their initial mass. This information emergence could occur through wormhole connections that become traversable as black holes evolve and their geometric structure changes during the evaporation process. Observational strategies for detecting black hole wormhole connections include searching for correlations between matter falling into black holes and phenomena occurring in distant spacetime regions, analyzing gravitational wave signals for signatures of wormhole geometry, and looking for deviations from classical black hole behavior that can indicate exotic interior structure. As you contemplate the possibility that black holes represent natural wormhole entrances rather than cosmic dead ends, recognize that this perspective transforms our understanding of these gravitational giants from isolated objects to connected components of cosmic spacetime architecture. Every black hole in the universe could be a cosmic gateway to distant regions or other realities, making these objects fundamentally more mysterious and potentially more important than classical physics suggests. But black holes represent just one potential source of natural wormhole formation. We must now explore how cosmic strings and other topological defects could create spacetime tunnels through high-energy physics processes that might occur throughout cosmic evolution.